So we are busy with voltaic cells, and one of the reactions that we did this morning was we placed a piece of aluminium into copper, and we saw that there was a change. There it is. This is what it looks like. You can see that the copper faded completely, and the aluminium turned into the blue solution faded, and the aluminium was changed to form aluminium 3+ ions. So I could use those chemicals to build a voltaic cell. So let's see what we would have. First, it is a spontaneous reaction. Between the aluminium and the copper ions, there will be a spontaneous reaction, right? So what energy is turned into what energy? What is the energy conversion here? Okay? It's a chemical reaction. So its chemical energy is converted into, there's a flow of electrons, so it will be electric energy. So in a voltaic cell, we've got a spontaneous redox reaction, and we have chemical energy converted into electrical energy or electricity. Why is that so? A redox reaction is a reaction where there's an electron transfer. Yes. Voltaic cell and a galvanic cell is exactly the same thing. So we could say galvanic cell, we can say voltaic cell. Same thing. Okay. What makes a galvanic cell? Okay. Good question. Let's build a voltaic cell. Let's say this is aluminium. And we place it into an electrolyte. This electrolyte contains, I need to be clever now. So this is aluminium, that one there, solid aluminium, and in here we have an electrolyte that contains aluminium ions. Let's say aluminium chloride. Hello. So the aluminium chloride. Thank you. Okay, so it's a solution. Now you need to listen carefully because I haven't mentioned this in class before. Metals are things with delocalized electrons. They flow around amongst the atoms. And good day. And the moment you put a solid piece of aluminium into a solution that's got positive and negative ions in it, that moment there is a potential difference between positive charge and the electrode. We can't measure that, but there is a potential difference between a metal and an electrolyte. So there is the tendency to want electrons to flow. Are you with me? It's brand new. It's the first time I'm saying this. When you put a solid piece of metal into an electrolyte, it wants to exchange electrons. Those aluminium ions, the Al3 plus ions, that will be in the solution, and the aluminium atoms in the metal, there's a potential difference. The one wants to take the other one's electrons. So there is a tendency to want the electrons to flow. But the electron flow between aluminium 3 plus and aluminium won't be able, you can't use that flow of electrons. And for every 3 electrons that comes from an atom, there will be one atom, there will be an ion coming out of solution, while there's an atom going into solution as an ion. You hear what I'm saying? So here you have Al3 plus wanting to take 3 electrons and making Al atoms, but the reverse reaction is also wanting to take place. Both these reactions want to take place. So there is a potential difference between the solid aluminium and the aluminium ions. Okay, let's connect this to a piece of copper. And we'll put a measuring instrument there called the galvanometer. Now the moment you put the piece of copper into a copper, let's say chloride, copper chloride solution, what will there be between the copper and the copper chloride solution? In here we've got a copper chloride solution. Let's change it to a red arrow. In here we've got a copper chloride solution, and that is our copper electrode. Okay? What will we have? We'll have the following wanting to take place. What? We'll have copper 2 plus wanting 2 electrons to form copper. Yes, ma'am?
Yes, ma'am.
But it's a reversible reaction, so copper also wants to go into solution. So once again, there's a potential difference. Between the solution and the solid. Now this solid we call the electrode, and the solution we call the electrolyte. The moment I join aluminium and copper, there's a wire through which electrons can flow. Why would electrons want to flow through that wire? Aluminium is in contact with copper. Aluminium is a what agent? Aluminium is a reducing agent. Copper is copper is a reducing agent. Aluminium is a reducing agent. Which one's the stronger reducing agent? No, don't guess. Take that table of reduction potentials and look which one is the stronger reducing agent.
Aluminium.
Aluminium is a stronger reducing agent So aluminium, when you join it to copper, it wants to give its electrons to copper ions. It's magic. Because aluminium is a stronger reducing agent than copper, copper is also a reducing agent, but it's the weaker reducing agent. So what happens, now we haven't completed the circuit yet, so there can't be any charge flowing here before the circuit is completed. So what do we need here? We need a salt bridge. So here we're going to put the salt bridge in there, and this salt bridge completes the circuit, and it prevents charge build-up in the half cells. So what will happen is aluminium will do what? Which reaction will take place? The forward reaction or the reverse reaction? Aluminium will then form aluminium 3 plus, and 3 electrons will be released by the aluminium atoms. So because aluminium is releasing the electrons, some people want to say that the aluminium electrode will be charged negatively because the electrons flows from the aluminium and they go to the copper wire. And the copper wire, to receive the electrons, the copper wire must be polarized positively. I hate this way of looking at it, because in reality it doesn't have a positive charge to it. The electrons are just flowing from the aluminium to the copper, because the aluminium is the stronger reducing agent, and the copper is in contact with the copper 2 plus ions in that electrolyte. So here the copper 2 plus takes 2 electrons to make copper. Okay? It's a spontaneous redox reaction, where this is called the oxidation half cell. Because that is where oxidation is taking place, and this is called the reduction half cell. Are you with me? Okay. So I haven't balanced this. If you balance, this must be multiplied by 2. And this must be multiplied by 3. We've done it earlier this morning. So the overall redox reaction is 2 aluminiums and 3 copper ions going to 2 aluminium ions and 3 copper atoms. Yes. Yes.
What do you mean when you say
There's a chemical change, so there is chemical energy converted into electricity because there's a flow of charge. This is the salt bridge. Help me. What's the salt bridge doing? It's completing the circuit. It's closing the circuit. And in the salt bridge, you'll, for example, have sodium ions and chloride ions. I'm choosing that as a salt for the salt bridge. Now, what happens to the concentration of aluminium ions in the oxidation half cell? what happens here? What happens to the concentration of the aluminium ions? Because of oxidation, what is happening to the concentration of aluminium ions?
It decreases.
I wear now.
Oh, it increases. with the
You
aluminium.
form aluminium 3+ ions. Aluminium goes into solution as aluminium 3+ ions. So what is happening to the concentration of the positive charge in the oxidation half cell?
Let me explain again, sorry, why the concentration is increasing.
It's forming aluminium ions. During the oxidation half reaction, aluminium ions are formed. So the concentration of the aluminium ions will increase.
In this solution, in the first solution, okay, the second solution right now.
This one.
Yes, ma'am. Okay, sorry, ma'am. So, the electrons go from this solution, the first solution.
From the aluminium, it goes to the copper, and when this copper electrode gets the electrons, the copper ions grabs them.
Okay.
So the copper ions grabs the electrons to form copper.
Which gains electrons, which makes it into
Yes, so what will happen to the concentration of the copper ions? What happens to the concentration of these copper ions as the cell works, as it gives electricity? You're taking copper ions out of solution. During the reduction half reaction, you're taking copper ions out of solution. So what happens to the concentration of the copper 2+ ions in the solution? It decreases. Are you with me?
No.
Okay. Talk to me.
I don't get for the copper solution. Why is the ions of the copper ion decreasing?
Because reduction is taking place. And reduction means a gaining of electrons. Who's gaining the electrons? Who is gaining the electrons? Copper 2+ ions. They're taking the electrons that's coming towards them, and they're making copper. So that removes the copper 2+ ions from the solution of copper chloride.
So, ma'am, the aluminium and also the copper has nothing to do with each other. It's just the electrons, the transfer of
The electrodes in this voltaic cell or galvanic cell, they are the electrodes. They are involved. The one is being eaten away and the other one is being growing. Because the copper here will come, this one will fall holes. Because of the atoms going into solution, this thing will be pitted. It will lose atoms. So more ions goes into solution. That's why aluminium ion concentration increases. Copper will deposit on this electrode, so its mass will increase, where the mass of the other one will decrease. It will have holes in it. It will become rough as the atoms goes into solution as ions. But here, the ions are taken out of solution to make copper. Are you with me now? Okay. So remember, we started off, for each aluminium ion, there were 3 chloride ions in there. You had chloride ions. 3 chlorides for every 1 aluminium. But now there are more aluminiums, more positive charges. So in here, this electrolyte will become positive because there are more positives going into solution. And what will happen here, where we have 2 chlorides, for every copper ion. What will happen here? We're removing the copper ions from the solution. So what's happening here in the copper half cell? It's getting an overall negative charge. Because you're taking the positives out, the negatives are staying there. Here, you've got your negatives, but you're putting more positives in. So what is happening is there is now a different kind of charge there. So this cell will stop working if you don't keep the overall charge in the electrolytes neutral.
So the reason why, you see the potential difference, the reason why it's the potential difference because this one is, because they're different from each other, as in like electrons are going away and one is electrons are
Going towards
going
it.
towards it. That's why it's a potential difference.
Yes.
Okay.
Now because of the more aluminium 3 plus in here, the chloride ions will diffuse through from the salt bridge. The chlorides will come here to keep them electrically neutral. And what will happen on the other side? What will go to this part where the positives are taken out of solution? The sodium ions will go there to try and keep the electrolytes balanced with the positive and negative charges. Are you hearing what I'm saying?
Yes, yes.
Okay, so that's the salt bridge.
That's the name of it.
The salt bridge is there to complete the circuit and to prevent a charge build up in the half cells. No, I'm not changing. I'm just wanting to answer the question. This is a voltaic cell. What is it used for? A battery is a voltaic cell. Here you've got chemicals that forms the electrolyte. The graphite there is used as the cathode and zinc is used as an anode. So they are batteries. Your car's engine won't start unless the battery gives that initial electricity needed for the starter to start the engine to turn. Yes.
And then what is the meter for? Is it
The galvanometer.
Yes.
It's like a voltmeter or an ammeter. It reads the galvanometer is like a voltmeter. It reads the potential difference between the electrodes.
So it tells us the amount of electrons that are being transferred
Well, you can calculate that.
by using the.
If you use an ammeter, you can calculate that.
Oh, because it has something to do with the electron.
Yes. The faster the electrons flow from the oxidation half cell to the reduction half cell, the higher the voltage supplied would be.
Now, how are we supposed to measure the electrode if it's a negative charged or positive charged? Because what she wrote there.
The stronger reducing agent will be the one that supplies the electrons, so that it will form the negative electrode. The stronger reducing agent will form the anode. The negative electrode where oxidation takes place. So the anode is the electrode where oxidation takes place, and the weaker reducing agent will form the cathode. So the cathode is where reduction takes place. So I want us to write down the cell notation. Now the convention is to put the oxidation half cell first and then the reduction half cell. So which one is the oxidation half cell? The aluminium half cell. And we start off with the electrode, and what happens to this electrode? It makes sense to me to start off with the electrode, because what happens here is aluminium is being oxidized to aluminium 3+ ions. So I start off with my electrode, and it is a solid, and it changes to aluminium 3+, which is aqueous solution, and then it's in contact with the reduction half cell. And what happens in the reduction half cell? Copper 2+ is reduced to copper. So here I write copper aqueous 2+, and a line between the electrode and the electrolyte. So Cu solid. So that is the cell notation for the copper aluminium cell. Okay. Next, I'm going to go to the board. You'll see something on the board there. And I want to explain that first before I'm coming back to this. So I want to show you how copper's electrode potential on the half cell is determined. What is the half cell, the electrode potential for copper on your table of reduction potentials? It's the copper going to copper 2+.
It's 0.16.
Are you sure?
Copper going to the copper 2+.
Yes.
0.16.
Copper and 0.16 is for copper 2+ to copper plus. Just go down a little bit. You'll see 0.34.
Isn't it the same thing?
Oh,
it's not.
I want to show you where that comes from. So they're called standard reduction potentials, and they are measured when the copper half cell is connected to the hydrogen half cell under standard conditions. Sorry, my line is going skew, but it's the idea that counts. So this is my copper electrode, and I connect it to the platinum electrode. There will be a what? An electrolyte that contains copper 2+ ions. In your half cells, the possible reaction taking place at the platinum electrode could be 2 hydrogen ions taking 2 electrons and forming hydrogen gas, or hydrogen gas breaking up to form 2 hydrogen ions and 2 electrons. Those are the 2 possible reactions that can take place in the hydrogen half cell. In the copper half cell, what are the 2 possible reactions that can take place? Copper 2+ plus 2 electrons can make copper, or copper can break up to make copper 2+ and 2 electrons. So they are reversible reactions. I'm stressing the fact that they're reversible reactions. Okay. There must be a salt bridge between the two electrolytes, otherwise no electrons will flow, and your salt bridge must contain a salt that will not make a precipitate, doesn't matter which electrolyte you have. So I'm going to take my easy way out and say sodium nitrate will be in my salt bridge, because no sodium salt will be insoluble, no nitrate salt will be insoluble. Next thing is to look to see which is the stronger reducing agent. Is the hydrogen the stronger reducing agent, or is the copper the stronger reducing agent? So, when we look at hydrogen copper, hydrogen is the stronger reducing agent. So the moment I connect the platinum to the copper, a spontaneous reaction is going to take place. That's what voltaic cells are about. So which reaction will take place here? Is it the two hydrogen ions plus 2 electrons going to hydrogen, or is it the hydrogen going to the ions? What is happening here? It will be the oxidation half reaction. Which is the oxidation half reaction? What is going to happen here? Oxidation is a loss of electrons. So the oxidation half reaction here will take hydrogen gas and break it up into hydrogen ions, and it will give 2 electrons. So these electrons, they come and they flow through the voltmeter and they come to the copper electrode. What will happen there? Reduction will happen here. So this is the reduction half cell. Okay, this is then the oxidation half cell. The hydrogen half cell is the oxidation half cell. And the reaction is Cu2 plus 2 electrons going to copper. Copper is a solid, copper 2 plus is in solution. Are you following me? Okay. So instead of drawing out this whole thing, I can use cell notation. To represent this cell. Oxidation always on the left hand side, reduction on the right hand side. What do I start off with? Yes, but what in the oxidation half reaction do I start off with? What would you find? No, listen. What would you find on the outer edges of the cell notation?
Electron.
Yes. What is the electrode in the hydrogen half cell?
Platinum.
Platinum. So we start with Pt, the electrode slash. Now, what's next? The H2. Gas, comma, hydrogen, ions. AQ. Double slash to take us to the reduction half cell. What is there? Cu2 plus in solution slash, because the copper is the electrode. So your electrodes, you start off and you end off with an electrode in the half cell.
Is it correct if I see it like the solids and the on each end?
That's right. What would the reading on this voltmeter be if we are working under standard conditions? standard conditions, because we have a gas, the pressure must be 101,3 kilopascals. The temperature must be 25 degrees Celsius. And the concentration of the electrolytes must be 1 mole per cubic decimeter. That's the condition that you can measure the cell potential. What is the cell potential measurements, do you think? A voltmeter won't measure it as negative, it will measure it as 0.34 volts. Okay. Now you're going to use this reading to calculate the copper's electrode potential. Under standard conditions. So our equation is the cell potential is equal to the cathode's reduction potential, cathode minus anode. Which electrode is the anode? The platinum is the anode. And the copper is the cathode. Okay? So the cell's measurement is 0.34 volts. The cathode is what we're looking for. So the electrode potential for the cathode is what we are looking for. What is the anode's electrode potential? The voltage there will be 0. It is taken as 0. And this is how we get the magic that the electrode potential for copper is, and that is copper going to copper 2 plus, or copper 2 plus going to copper, is 0.34 volts. The reading that you see, that is listed on the table of reduction potentials. Okay. I have explained it on the green board, but I want to, just for the sake of the video, show you the aluminium half cell connected to the hydrogen half cell. And here I'm going quicker now. I'm not going to go with a drawing. So which one is the stronger reducing agent? Aluminium or hydrogen? Aluminium is the stronger reducing agent. So with that, aluminium will be forming the oxidation half cell. Right? So aluminium will go and form aluminium 3 plus ions, and 3 electrons will be taken from it. Okay? And the hydrogen half cell, this one, the hydrogen half cell, will be my reduction half cell. The aim of the game is to get the electrode potential for aluminium. I want the electrode potential for the aluminium. That is what I want. And to get it, I connect the aluminium half cell to the hydrogen half cell under standard conditions. Got it? So what happens to the hydrogen half cell? Which reaction will take place? Reduction. So what happens there is hydrogen ions will take 2 electrons and make hydrogen gas. Have I got it right now here? Okay. It is hydrogen ions going to hydrogen. Now, the electrode potential for the hydrogen half cell is 0 volts. It's taken as 0 volts because you can't measure it. So it's like choosing the direction of electric current to be that of conventional current. Okay? Now, your cell notation will be taking the oxidation half cell, Al. Although it will be oxidized, it is also the electrode / it goes to Al3 plus Aq and double slashes for representing the salt bridge between the electrolytes. And on this side, you've got the hydrogen ions going to hydrogen, and here, because it's not between a liquid and a solid, or a solution and a solid, it's between a gas and a solution, I put a comma. That is different from what we have done before, and / my platinum is the electrode in the reduction half cell. To get my electrode potential for aluminium, the cell potential is what will be measured by the voltmeter between the aluminium and the platinum, and it is E cathode, the electrode potential for the cathode, minus the electrode potential for the anode, and that the cathode is what? Which one is the cathode? Platinum or aluminium? This will be the reduction half cell will be containing the cathode. Cathode is the electrode where reduction takes place, and the aluminium would be my anode. Okay. So cathode's electrode potential is taken as 0 volts. The voltmeter's reading will be 1,66 volts. What is the electrode potential for the aluminium / aluminium 3 plus? It will be minus 1.66 volts, and that is tabulated on the table of reduction potentials. So I have shown you now where those readings, those values are coming from. That's what I've shown you. Now I want to show you where cell potentials will come from when we have the aluminium and the copper joint. Let's go back there. You see, we had a copper aluminium cell. Okay. What is the standard cell potential for this cell? Is my question. And then we'll end the lesson there. So what I've shown you is I took the copper and I jointed it to the hydrogen half cell, and we measured 0.34 volts. And we took the aluminium under standard condition, connected it to a hydrogen a hydrogen half cell, and we got a measurement, calculated the electrode potential as minus 1.66 volts. Now, if I connect the copper and the aluminium, what will the cell potential be? That's a big question, so I'm going there now. So what is the copper aluminium cell potential under standard conditions? Now, let's just orientate ourselves again by looking at the cell notation. What here will be oxidized, copper or aluminium? And you can turn back in your books because you've made the notes. Which is the stronger reducing agent? Aluminium. So the anode, where oxidation is taking place, is the aluminium turning into aluminium ions. Yes. Then the cathode is where reduction will take place. That is the copper 2 plus going to copper. Okay, so what is the cell potential? What is the cell potential? E cell. Have you discovered this equation on your data sheet? You'll see, I think there are 3 equations. I'm just used to using this one. Please look on your data sheet and copy the equation as it is. E cell is E cathode minus E anode. No? So the cathode's standard electrode potential is 0.34 volts, and the anode's standard electrode potential is minus 1.66 volts. So it is 0.34 minus 1.66. What is the value there? 2. So under standard conditions, the copper aluminium electrolytic or not voltaic cell or galvanic cell will give you 2 volts. Now I'll tell you the last secret for today. If the cell potential is positive, it means that the redox reaction is spontaneous. And I'll end there. So we'll carry on from here. Then we will do examples where we need to look at the reversibility of the reaction and its effect on the cell potential, and we also need to look at non-spontaneous redox reactions.